Hi, we're going to talk today about the Doppler effect. We talked about this a little bit in class. We're going to continue and talk about how to solve problems having to do with the Doppler effect. So, as you may recall, if you have a sound signal on a source that is sitting still, it's very simple. Here I have a car, and there's some kind of a siren or a bell or something coming off. Could be an ice cream truck. I don't know. Could be a police car. Gotta check. But in any event, if it's standing still, it's not a big deal. The sound waves come off in this circular pattern. We've talked about this before. Each of these lines represents a wavelength. The interval between the lines shows the frequency, how frequently a wave comes out of there. The frequency is related to the pitch of the sound that you actually hear. Here, the car is sitting still. Not a big deal. It's very simple. V is the speed of the sound. You can see it here. It's represented as a ray, which is coming off perpendicular to the wavefront. Okay, let's go over here. Now, my car is moving forward like this. The speed is called V sub s, the speed of the source. As I move forward, as my car moves forward, you can see, okay, now the speed of each sound wave coming off the front of this car is enhanced by the speed of the car. That means that the actual observed speed is the speed of the sound wave plus the speed of the car, which we're calling V sub s. That makes this guy look asymmetrical in this way. So you see, in the direction of the motion, the frequency appears to be higher, so it'll be a higher pitched noise. Whereas if you're on the other side of the car, these little figures represent observers. If you're on the other side of the car, the speed of the sound reaching you is the speed of the original sound minus the speed of the car. Because as you can see, I'm moving away from you, so I am pulling those waves back from you even as I'm sending them towards you. Very mixed message, but this is life. These things happen. So from the front of the car, you hear a higher pitch noise, higher frequency, higher pitch. From behind the car, you're going to hear a lower pitch noise, lower frequency, lower pitch. That's the Doppler effect. It doesn't just happen with sound, it happens with light. It's a wave thing. Anything can generate waves. We have a lot of waves in our world. Those waves create whatever phenomenon you're detecting, whether it's a sound or a light. Well, let's talk about sound. Let's do it sound. Okay, so the equation we have to represent all this gives us the frequency that the observer, we use D instead of O, because a subscript O could look like a 0. So instead we use F sub D. I know it's hard to see in this video. F sub D is the frequency perceived by the detector. That's the little person standing near the car. Hopefully not right in front of the car that's moving toward them. We'll trust them to handle that, get out of the way in time. Okay, so the frequency of the detector is a modified version of the frequency of the source. So this is the frequency of the source right here. It's the pitch of the sound if nobody was moving. So now, not only could the car be moving, but the person could be moving too. Like two cars coming at each other on the freeway. Then you have to account for the velocity of the observer as well. So here's our equation. It's given to us. We're not deriving it. The frequency of the detector is equal to the frequency of the source times this fraction. Let's walk through it. Velocity of the sound minus the velocity of the detector over the velocity of the sound minus the velocity of the source. So let's see what happens. So let's say the detector's not moving, but the source is. That happens. That's what the scenario was that we started with. So this means V sub D, oh, come on. Work with me here, pen. V sub D equals 0. Okay? If V sub D is equal to 0, what happens to this equation? If frequency of the detector equals the frequency of the source times v minus v sub d, but v sub d is 0, so it's just v, divided by v minus v sub s. Well, v sub s is not 0. We can't just get rid of it. So we can simplify this guy. How are we going to do that? Well, we could divide the whole thing through by v. So that would be v over v minus. It's an algebra thing. We can do this. We multiplied this whole thing by 1 over v over 1 over v. Okay? So now v over v is 1. Okay, so here I have the frequency of the detector, frequency of the source. That doesn't change. The whole reason we're doing this is we're going to get a fraction here that modifies the original frequency of the sound. So this gives me 1. V over v is 1 over 1 minus v sub s over v, the original v. So that's an equation that I can use in order to calculate what happened to my frequency. So let's see how this goes. Let's say the frequency of the source is 256 hertz. The speed of sound at room temperature, ordinary circumstances, is 343 meters per second. And let's say the car is moving at 50 miles. No, we don't do miles. No miles. We'll do 20 meters per second. Okay? So that means the frequency of the detector will be equal to 256 hertz times this fraction, 1 over 1 minus. V sub s is 20 meters per second divided by 343 meters per second. That's a big fancy fraction. Let's get out our calculator if we can find it. I use the one on my phone. It's 5/8. We've got two significant. You still with me? Okay. And we add that to 1. And that gives me 1 over 0.94. All right. We invert that and we get 256 hertz times 1.06. With sig figs it would be 1.1, but let's just do this. Times 256. That gives me 270 hertz. It's really 271.9, but we don't have that many significant figures, so let's just say 270. Okay, so what happened here? Let's see if this makes sense. So what I'm finding is that my car is moving toward me, the observer, at 20 meters per second. And that means what? Think about it. Is that frequency going to be higher or lower? Now wait, you just think about it and let me know what you think. Right, it's higher. The car is moving at this speed, the waves are coming off, and so that's enhancing the frequency, the speed of the waves. So it turns out that that's the result we got. It is a little bit higher. So you're going to hear a higher pitched sound because the car is moving toward you.